Hello students, welcome back to session 8 of Hilbert spaces. So in this class, let us study what's meant by projections on a linear space and projection on Hilbert spaces. Okay, suppose L is a linear space. L is a linear space, and this linear space L is the direct sum of its subspaces, say M and N. Suppose a linear space L is the direct sum of its subspaces M and N. Then every vector Z belongs to L can be uniquely written as Z is equal to how x plus y, where x is an element of M and y is an element of N. Okay, so every Z belongs to L can be written as Z is equal to x plus y, where x is an element of M and y is an element of M. The projection on M, the projection on M along N, the projection on M along N is a linear transformation, E from L to L. Means the projection on M along N is a linear transformation E on L defined by E of Z is equal to X. E of Z is equal to X. Understand this? The projection on M along N is a linear transformation E from L to L such that E of Z is equal to X. E carries every element of L to maps to X. Okay, so this is the projection on M along N. So clearly this operator E is linear. So that we can show it now. Say let Z1 and Z2 be any two elements of L. Then what will happen? Z1 will look like x1 plus y1 and Z2 will look like x2 plus y2, where x1 and x2 are elements of M and y1, y2 are elements of N. Now E is a projection on M along N means what will happen? E of Z1 is equal to x1 and E of Z2 is equal to x2. Also M is a linear subspace of L because M and N are both linear subspaces of L. Therefore, if x1, x2 belongs to M means the linear combination alpha into x1 plus beta into x2 belongs to M. Okay. So similarly, alpha into y1 plus beta into y2 belongs to N. Okay. Now consider E of alpha z1 plus beta z2. So this is equal to E of alpha into z1 is x1 plus y1 plus beta into z2 means x2 plus y2. So this is equal to E of alpha x1 plus beta x2 plus alpha into y1 plus beta y2. So this is equal to alpha into, because this is an element of M means E of x plus y is x. So accordingly alpha into x1 plus beta into x2. So this is equal to alpha into x1 can be written as E of z1 plus beta into x2 can be written as E of z2. Therefore, E of alpha z1 plus beta z2 is equal to alpha times E of z1 plus beta times E of z2. Therefore, E is a linear transformation. E is a linear transformation. That is, projection is a linear transformation. Okay. So now let's prove few results on this topic. Say first one is, say I'll take, suppose a linear projection E on a linear space L is a projection on some subspace if and only if it is idempotent. A linear transformation E on a linear space L is a projection on some subspace if and only if it is idempotent. Idempotent means E square is equal to E. Okay. So first, now let L is equal to M1 plus M2. Okay. Let L be the direct sum of its subspaces M1 and M2. And let E be a projection on M1 along M2. Let E be a projection on M1 along M2. So now we have assumed that E is a projection and we will show that E is idempotent operator. So for this, let X belongs to L be any arbitrary element. Then X looks like x1 plus x2, where x1 is an element of m1 and x2 is an element of m2. By definition, what will happen? E of x is equal to x1. You call by this number 1. Now e square of x is equal to e of x, that's equal to e of x can be written as x1. So e of x1 can be written as e of x1 plus 0, where 0 belongs to m2. Okay, so e of x1 plus 0, where 0 belongs to m2 implies this is equal to x1. x1 is what? E of x. Therefore e square of x is same as e of x. This implies e square is equal to e for every x belongs to L. Now e square is equal to e means e is a idempotent operator. Okay, so we have assumed that e is a projection and we have shown that e is idempotent. Now conversely, let e be a idempotent operator so that e square will be equal to e. Let M1 be the subspace of L containing elements of the form e of x is equal to x, means M1 contains set of all x belongs to L such that e of x is equal to x. Okay, and M2 is equal to set of all x belongs to L such that e of x is equal to 0. Means what? M2 will look like the null space of E. M2 is the null space of E. Then clearly you can see that M1 and M2 are subspaces of L. That you can verify it easily. M1 and M2 are subspaces of L. Now we show E is a projection on M1 along M2. Actually our aim is to show E is a projection. So we are going to show E is a projection on the subspace M1 along M2. So for this what you have to do? So first we have to show that L is the direct sum of M1 and M2. Okay, first let us show this. Now any x belongs to L can be written as, look here, any x belongs to L can be written as x is equal to, can I write it as e of x plus x minus e of x. Okay, so this is equal to, let x1 is equal to e of x and x2 as x minus e of x. Now e of x1 is equal to what? E of x1 means e of x, that's equal to e square of x, but we have assumed that e is idempotent, therefore e square is e itself, e of x is x1 again. Now e of x1 is equal to x1 means what? Where x1 lies? x1 lies in m1 because m1 contains set of all x belongs to L such that e of x is equal to x. Therefore e of x1 is equal to x1 implies x1 belongs to m. And e of x2 can be written as x2 is x minus e of x. So e of x minus e of x means e square of x. But e is idempotent, so e of x minus e of x, which is 0. Now e of x2 is 0 means according to definition of M2, x2 belongs to M2. Thus we have taken x belongs to L and we have shown that x can be written as e of x plus x minus e of x, where e of x belongs to M1 and x minus e of x belongs to M2. Therefore every element of L been written as a sum of an element of M1 plus sum of an element of M2. Now, so therefore we can declare that L is the sum of M1 plus M2. You call by this number 1. Next, suppose we have an element x belongs to M1 intersection M2. This implies x belongs to M1 and x belongs to M2. Now x belongs to M1 implies what? E of x is equal to x itself. And x belongs to M2 means e of x is 0. Now e of x is equal to x and e of x is equal to 0 implies what is the possibility? Ex must be 0. Therefore M1 intersection M2 contains only 0. Only 0. Then by definition of a direct sum, what will happen? Now L is the direct sum of M1 and M2 and M1 intersection M2 contains only 0 vector means then by definition of direct sum L is the direct sum of M1 and M2. L is the direct sum of M1 and M2. Okay. Now let's come to this. Now let us show that E is a projection on M1 along M2. For this, let x belongs to L. Then x can be written as x1 plus x2. Just now we have shown, where x1 is an element of M1 and x2 is an element of M2. Now consider E of x. E of x is equal to what? E of x1 plus x2. So this is equal to E of x1 plus E of x2. E of x1 is what? x1 itself. E of x2 is 0. Therefore, x1 plus 0 is x1 itself. Therefore, E of x is equal to x1 means what? Then we say by definition of a projection, E is a projection on M1 along M2. So we have assumed that E is idempotent and we have shown that E is a projection on M1 along M2. Okay. Now let us take next result. Suppose E is a projection on a linear space L. Suppose E is a projection on a linear space L. Then the range of E means set of all elements belongs to E, which are the images of E. Set of all elements belongs to L, which are the images of E. Okay. Then the range of E equals the set of all vectors which are fixed under E. Set of all vectors which are fixed under E means what? So range of E is set of all x belongs to L such that E of x is equal to x. E of x is equal to x means what? Yes, which are fixed under E. Right? So yes, proof we have. Range of E is, by definition of a range, what? Range of E is set of all x belongs to L, which are the images. Okay, set of all x belongs to L such that x is equal to E of y for some y belongs to L. Because look here. So if E is a mapping from L to L, so where E of L lies? E of L will be subset of L itself. Okay, range of E. Range of E means what? Range, say this is domain, this is codomain. So say this is the A vectors here. So those vectors which are, so this is range of E. Say if this maps to here, say here only. So this is range of E, this is range of E, and we have left with other elements, that is the codomain. Okay. So range of E means set of all vectors in E. Range of E is what? Set of all vectors, say x belongs to the image space L such that x is the image of some element y, where y belongs to domain space, where y belongs to L. Okay, understand now? So range of E is set of all x belongs to L such that x is equal to E of y, where y belongs to L. So this is, we have taken, this is the definition of range of E. Now range of E is, we have to show it is nothing but set of all x belongs to L, E of x is equal to x, we have to show this. And let M be set of all x belongs to L such that E of x is equal to x. So means M contains set of all x belongs to L which are fixed under E. Set of all those vectors belongs to L which are fixed under E. What we have to show? We have to show R of E is nothing but M. R of E is equal to M. Say for this, let x belongs to R of E. If x belongs to R of E, then by definition there exists some y belongs to L domain space such that E of y is equal to x. Now E square of y is equal to E of y. E of y means according to this it is x, E of x. This implies E of y is equal to E of x. This implies E of y is what? X. X is equal to E of x. Now x is equal to E of x means what? X belongs to M. Now x belongs to R of E and we have shown that x belongs to M. Therefore range of E is contained in M. So let us prove the converse part. Now let x belongs to M. Then by definition of M, what will happen? E of x is x. Now E of x is x means we see that x belongs to L is such that x belongs to L codomain space. X belongs to L is such that x is the image, x is the E image of x belongs to L. Means if x belongs to codomain space or range of E, then there exists some x belongs to the domain space such that the image of that element is this. Therefore by definition what will happen? Therefore x belongs to range of E. X belongs to range of E. Now x belongs to M and x belongs to range of E means what happens? M is contained in R of E. Already we have shown R of E is contained in M. Therefore R of E is nothing but M. Means range of E is nothing but the set of vectors which are fixed under E. Okay, we have shown that range of E is equal to set of all x belongs to L such that E of x is equal to x itself. Now let us take up the other result. Suppose a linear transformation E is a projection if and only if I minus E is a projection, complement of this. So if a linear transformation E is a projection if and only if I minus E is a projection, that is if E is a projection on M1 along M2 where M1 and M2 are subspaces of E, subspaces of L, okay, then I minus E is a projection on M2 along M1, means if E is a projection on M1 along M2, then I minus E is a projection on M2 along M1. Okay, let us prove this. First let E be a projection. Let E be a projection such that E is a projection on M1 along M2. So now E is a projection, then what will happen? E is a projection means it is an idempotent operator. We have proved this. So E square is equal to E. Now I minus E square. Now I minus E whole square is I minus E into I minus E. If you make a product, this is I into I square minus I into E minus E into I plus E into E square. So that's equal to I square is I itself minus E, I into E is E minus E into I is E plus E square is E itself. Therefore, what will happen? I minus E, so plus E minus E get cancelled. So this is I minus E. Therefore, I minus E whole square is equal to I minus E, means I minus E is idempotent. If I minus E is idempotent, then we declare that I minus E is a projection. So if E is a projection, then I minus E is also a projection. Conversely, let I minus E be a projection. What we have to show? E is a projection. Okay. Now I minus E is a projection implies what will happen by definition? I minus E whole square is equal to I minus E. So I minus E whole square means I minus E into I minus E is equal to I minus E. Now again multiply this. So I into I square is I itself, I square minus E plus E square is equal to I minus E. Okay, because E into I is E, I into E is E plus E square. Now I minus E on the both sides there, therefore I minus E get cancelled. So this implies minus E plus E square is equal to 0. This implies what? E square is equal to E. Now E square is equal to E implies what? E is a projection. Thus we have assumed that I minus E is a projection and we have shown E is a projection. Thus E is a projection if and only if I minus E is a projection. So now let us take up. Suppose E is a projection on M1 along M2. E is a projection on M1 along M2. Then what will happen? L is the direct sum of M1 and M2. Definition you know it. And every x belongs to L can be written as x1 plus x2, where x1 is an element of M1 and x2 is an element of M2. And E is a projection on M1 along M2 means what? E of x is equal to x1. Now you consider I minus E of x. I minus E of x is what? I of x minus E of x. I of x is x itself because I is the identity operator, x minus E of x. Now x minus E of x can be written as x minus E of x is what? x1. E of x is x1 because E is a projection on M1 along M2. So now x is equal to x1 plus x2 means x minus x1 is what? x2. Therefore I minus E of x is x2 means what? By definition I minus E is a projection on M2 along M1. So we have shown that if E is a projection, then I minus E is also a projection. Further, if E is a projection on M1 along M2, then I minus E is a projection on M2 along M1. It reverses. Okay. So these are the few results for this class. Thank you for listening.